Thermodynamics Gas Laws. Some questions to ponder. How are pressure, volume, and temperature related in a gas? And what is the ideal gas law? What is Boyle's law? What is Charles' law? What is Gay-Lussac's law? Why is Kelvin used to measure temperature in a gas? And what is absolute zero? We're going to be taking a macroscopic view of gases. Instead of trying to chase these little teeny particles around individually, we're going to look at the quantities of volume, the type of gas and how much gas there is, the pressure associated with trying to contain those gases, and then the temperature of the system as well. So these are our macro system quantities that we're going to be working with to establish our gas laws. We're going to start off with an idea or the relationship between pressure and volume, and that's known as Boyle's law. To do this, we're going to keep the amount of gas constant within our container here. So the number of particles within the gas particles within this container is going to stay the same. The system is going to be a closed system. We're also going to keep the temperature constant, meaning that we're not going to add or take away heat from this system. That being the case, if the volume of the system increases here, we make the container bigger and bigger, we can see that the particles have more space between them. So their rate of collisions when they're bouncing against each other, when they're bouncing against the sides of the container, the walls of the container, the rate of collisions is going to decrease. And because of that, the amount of force per area on the container walls on the inside decrease, and the pressure will decrease. So as the volume increases, the pressure will decrease, and that's an inverse variation. So in other words, with a small container here, small volume, we get a higher pressure, and then as the volume gets bigger, the pressure gets smaller and smaller. And so that's our inverse variation. We represent that inverse variation this way. Pressure is inversely proportional to volume. In other words, as the volume gets bigger, the overall pressure will decrease, or will increase rather, and vice versa. So if we look here, as the volume decreases, if we keep, we can make this proportion equivalent if we take all the other parts of the system, in other words the amount of gas and the temperature and everything else, and we make those things all constant as we did in this example. If we increase the volume, we're going to be dividing by a bigger and bigger number, so the pressure is going to get smaller and smaller. Now if we multiply both sides by the volume here, then we can get another way we represent this inverse variation, and that is in this particular configuration, pressure times volume is a constant. So again, as the volume increases, the pressure has to decrease proportionally in order to keep everything else in the system constant. And Robert Boyle, with his lab assistants, figured that out in the mid-1600s, quite a while ago. Our next relationship to take a look at is a relationship between volume and temperature, and that's Charles' law. So if we are we're still keeping the system closed. We have the same amount of particles in this sealed container here, and it's sealed with a piston that can move upward, and that piston moves upward in order to keep the pressure constant. But now we no longer have an isolated system because we're going to heat the system here and add heat to this system as we go. And as we add heat, we can see that the volume is going to increase. So we get this graphical relationship. As the temperature increases, the volume increases linearly. So for each chunk of temperature rise, we get an equal chunk of volume rise. And so, quite simple relationship, but volume is directly proportional to an increase in temperature. And that is Charles' law in around the 1780s. So we're going to take a look at Charles' law in action.
The volume of a gas is directly proportional to its absolute temperature. This is referred to as Charles's law. Room temperature is about 293 kelvins.
Before we move on to our next relationship, let's stay with volume temperature and let's see where we come up with a new temperature scale called Kelvin. If we have our volume temperature relationship here from Charles' law, we can see that if we remove heat from the system, the overall volume is going to decrease and decrease, and we continue to remove heat, and cool the system, that eventually get to a point where it's not practical to cool the system anymore. We can't really cool it anymore. But what we can see here is if we follow this line, its trajectory down, that it would, if we could cool it down further and further, we would reach this temperature line right back here, 273 degrees Celsius lower than zero, freezing of water. So Lord Kelvin said, since that is kind of our zero place for volume and temperature, that should be our scale that we use in thermal systems, a scale reference to zero back here. And so that is what we do. We created a new system called Kelvin. And so we create 0 Kelvin back here, 273 degrees below 0 Celsius. Therefore, 0 Celsius is 273 degrees Kelvin, since a degree Celsius is equal to 1 Kelvin. And likewise, 100 degrees Celsius is equivalent to 373 Kelvin. Notice that we don't put degree Kelvin, and it's just called Kelvin. So 1 degree Celsius is equal to 1 Kelvin, and that is our Kelvin scale. And way back here, the 0 Kelvin is called absolute zero, where theoretically all particles would stop moving, which is not possible, but it's a good theoretical reference point for our work. Now we can move on to our next relationship. If we have if pressure and volume were related, and temperature and volume were related, then pressure and temperature should be related, and it is through Gay-Lussac's law. I didn't do a good job of illustrating this necessarily. We're going to keep the amount of gas constant, so it should the same number of particles are on each of these containers. I just tried to show the different velocities of those particles, and in trying to reduce the velocities of those particles, it makes it look like there are less particles, but there's same amount of particles in each of these containers, and the container is the same size. So in our picture here, if we reduce the temperature, it reduces the thermal kinetic energy of these particles, and therefore they're not traveling as fast or colliding as vigorously with each other, nor are they colliding with as much force on the inside of the walls as they would if they were traveling faster at a higher temperature with a higher thermal kinetic energy. So with a reduced temperature here, we get reduced collisions and reduced pressure, and we can follow that similar line. It would be a similar line to the one we saw with volume temperature, similar relationship, and if we follow that down again, we would get to a point where there would be zero pressure at 0 Kelvin down here. So we get our Gay-Lussac's proportionality here. The pressure is proportional to temperature. And we can take a look at that relationship next.
Zero degrees Celsius. Dry ice bath. Liquid nitrogen bath for low temperature measurement. Getting a data point for pressure and temperature, 100 degrees Celsius. Getting a data point for pressure and temperature, 0 degrees Celsius. Getting a data point for pressure and temperature, minus 79 degrees Celsius. Getting a data point for pressure and temperature, minus 196 degrees Celsius.
The last idea we need to create our gas law is an idea which comes out of Avogadro's hypothesis. And we had our volume temperature relationship and our pressure temperature relationship here. Now, if we combine all of those ideas here, and we want to take a look at what happens in a system where we increase the number of particles. So now we don't have the same number of particles. We're going to increase the number of particles from one system to another system. And so let's take a look at our volume temperature. If we add a certain number of particles N1 here of gas, and we would get this relationship with volume temperature. If we increase the number of molecules and looked at temperature with a higher number of particles, everything else being the same, we would get a steeper graph of volume versus temperature when we had more particles in the container. We could get the same or similar graphs for pressure too by increasing the number of molecules or particles within a container. So the slopes of these graphs that we had done previously would increase with an increase in number of molecules here. In other words, if we go back, pressure is proportional to not just the temperature, but also it's proportional to the number of particles in the container. Same is true for volume. So now we're going to put it all together. When we put it all together, our pressure and volume and temperature with our pressure volume Boyle's law. So we have Boyle's law and Charles' law and Gay-Lussac's law, and we put those all together, we can see that pressure volume here is proportional to the number of particles times the temperature. And then we can actually make that proportionality equal if we put in a proportionality constant. And that proportionality constant is known as a universal gas constant. In other words, it doesn't vary. It's always the same value. And there we have it. That is the ideal gas law. One other comment here. Usually a proportionality constant is the first thing in this, but historically the number of particles is in front of the proportionality constant here for whatever reason. So you'll hear this often, PV equals nRT, especially when you are in a chemistry class. You'll hear that a bunch. PV equals nRT, and that is our ideal gas law. So hopefully after all this, you can see how pressure, volume, and temperature are related in a gas and what the ideal gas law is. What Boyle's law is, Charles' law, and Gay-Lussac's law, why Kelvin is used, and what absolute zero is. Scratch's parting idea. Hopefully you aren't too gassed to strive for continuous improvement.